Welcome to Spring LIB.
31.80. So we have a series RLC circuit that's being driven by a source that has a frequency of 400 hertz and an EMF amplitude of 90 volts. We have the given component values here. First, we'd like to find the RMS voltage across each of the components, and then we want to find the average rate at which energy is dissipated. So before we get started finding the RMS voltage, it helps to find the reactances of the two reactive components. So the reactance of our inductor is 2 pi FL. This is 60.82 ohms. The reactance of the capacitor is 1 over 2 pi F C, 32.88 ohms. And we know the resistor is 20 ohms because we're just told that. And so now the current amplitude is going to be the EMF amplitude divided by the net impedance. Which actually we should write down first. So the magnitude of the net impedance is the square root of R squared plus XL minus XC squared. Which is 34.36 ohms. So now the current amplitude is the EMF amplitude divided by that impedance, like we said earlier, and that has a value of 2.62 amps. And we want the RMS current to find the RMS voltage. And so you divide this by the square root of 2, and so the RMS current is 1.85 amps. So the potential difference RMS across the resistor is going to be the RMS current times the resistance. That will be 37 volts. For the capacitor, it'll be the RMS current times its reactance. Which will give us 60.9 volts. And for the inductor, same story. I RMS times the inductive reactance. And that gives us 113 volts. So the power being dissipated, or the average rate at which energy is dissipated, which is the average power. The resistor is the only thing dissipating any energy. So this is going to be the RMS current squared times the resistance. And that gives us 68.6 watts.